Have you ever wondered how structures like skyscrapers or bridges withstand forces from the environment and usage? The answer lies in the intricate and fascinating field of structural analysis. This is the science of predicting how structures behave when subjected to various external loads, and it's crucial for ensuring the safety, efficiency, and functionality of the structures we rely on every day. Imagine a skyscraper rising high into the sky, a marvel of modern engineering. It's not just standing there by chance, it's the result of detailed structural analysis, taking into account the weight of the building itself, the people and objects inside it, and the environmental forces acting on it, such as wind and earthquakes. Or consider a bridge spanning a river carrying heavy traffic. It must be designed to handle the weight of the vehicles, as well as the dynamic forces when they move across it, not to mention the effects of weather and changing temperatures. And it's not just about the big picture. Structural analysis involves looking at each individual component of a structure, the beams, columns, frames, and trusses, and understanding how they interact to support the overall structure. Each of these components has a role to play. The beams span spaces and carry loads down to the columns. The columns, in turn, transfer these loads to the foundation. Frames are essentially a network of beams and columns, and trusses are special structures that are highly efficient at supporting loads. So, what's the goal of all this analysis? It's to ensure that when a structure is subjected to loads, it doesn't deform or fail. It's to ensure that the building you're in right now, or the bridge you drove over earlier, is safe and able to do its job effectively. Engineering structures to withstand these pressures is no small feat, and that's where the science of structural analysis comes in. How do engineers determine the kind and amount of forces a structure can withstand? This question leads us to the concept of load factors. Just like your backpack feels heavier when loaded with textbooks, structures also feel the weight or load of various forces. Load factors are essentially weight multipliers that engineers apply to these loads. You might be wondering what these loads are. Well, they come in various forms, such as gravity pulling the structure downwards, wind pushing against it, or even the weight of the people and objects the structure supports. Let's break this down further. We have dead loads, which are permanent or static. Think of the weight of the structure itself, like the concrete, steel, or wood that make up a building. These materials don't change their position or disappear suddenly, hence the term dead load. Next, we have live loads. These are temporary or dynamic loads that change over time. The weight of furniture, people, and vehicles that move in and out of a building are examples of live loads. Lastly, we have environmental loads. These include natural forces such as wind, snow, earthquakes, and even temperature changes. Ever noticed how materials expand in the heat and contract in the cold? That's an environmental load right there. All these loads individually and combined can exert a significant amount of stress on a structure, and that's where load factors come into play. By multiplying the estimated loads with these factors, engineers can predict the maximum forces a structure might need to withstand during its lifespan. These factors are critical in determining how a structure responds to external forces, and they form the basis of structural design. What happens when these forces act on a structure, you might ask? Well, to understand that, we need to delve into the concept of stress distribution. Stress distribution is all about how forces are spread within a structure. It's the internal equivalent of the external loads we've been talking about. Think of a sponge being squeezed. The pressure you apply with your hand is the external load. But what happens inside the sponge? The force is distributed throughout, creating internal stress. The same principle applies to structures, from bridges to skyscrapers. Now, if the stress is evenly distributed, all is well. But what if it isn't? What if there's a weak point where the stress concentrates? That's when things can go south. Uneven or concentrated stress can lead to weak spots or even failure. Imagine pressing your thumb into the sponge instead of squeezing evenly. You'd see a concentrated dent, right? That's a stress concentration, and it's not something you want in your structures. Let's take a real-world example. Ever noticed how bridges arch gracefully over rivers? That's not just for aesthetics. The arch distributes the weight of the vehicles evenly along the length of the bridge, reducing stress concentrations and making the bridge stronger. But stress distribution doesn't just apply to grand engineered structures, it's everywhere. When you stand, the soles of your feet distribute your weight over the ground. When you wear a backpack, the straps distribute the load across your shoulders. In essence, understanding stress distribution is vital in maintaining the structural integrity of everyday objects and engineered structures. It's a complex balancing act that engineers grapple with every day. So, the next time you marvel at a towering skyscraper or drive over a sturdy bridge, remember the intricate dance of forces at play within. How do engineers ensure that structures remain safe even when subjected to unexpected loads? Safety is paramount in engineering, and one of the key ways engineers ensure this is through the inclusion of safety margins in structural design. Safety margins, simply put, are buffer zones. They account for uncertainties, both in the loads a structure might encounter, and the strength of the materials used in its construction. Imagine you're designing a bridge. You've calculated the maximum load it will likely bear, including cars, trucks, and even the occasional parade float. But what if something unexpected happens? What if a construction crew parks their heavy machinery on the bridge, or a once-in-a-hundred-year storm hits? This is where safety margins come into play. Safety margins are like a safety net, designed to catch these unexpected events. They ensure that structures can handle more than the everyday pressures, more than the anticipated loads. They're the extra bit of strength engineers build into their designs, allowing structures to withstand unexpected or extreme events without collapsing. In essence, safety margins are all about preparedness. They're the engineering equivalent of packing an umbrella even when the weather forecast only predicts a 10% chance of rain. Because when it comes to structural design, it's always better to be safe than sorry. Let's not forget these safety margins are not just pulled out of thin air. They're carefully calculated based on a myriad of factors, including the properties of the materials used, the expected lifespan of the structure, environmental conditions, and even the potential consequences of a structural failure. So the next time you're crossing a bridge or stepping into a skyscraper, take a moment to appreciate the meticulous planning and careful consideration that goes into ensuring your safety. It's not just about making structures that stand up, but about making structures that stand up to anything. Safety margins are an integral part of structural design, ensuring that structures can withstand more than just the everyday pressures. So, we've learned about structural analysis, load factors, stress distribution, and safety margins. But how do these all come together? Let's take a quick recap of our journey. We began with structural analysis, the science of predicting how structures respond to external loads. This intricate process involves understanding the components of structures such as beams, columns, frames, and trusses, and how they all work in unison to support and distribute loads. Then we ventured into the world of load factors. These multipliers applied to loads like wind, gravity, or live loads play a vital role in structural analysis. They consider dead loads, which are permanent, live loads, which are temporary, and environmental loads like wind and snow. Next, we decoded stress distribution, which refers to how forces spread within a structure. The importance of this can't be overstated, as improper stress distribution can lead to weak spots or even failure in a structure. Engineers meticulously analyze stress distribution to maintain structural integrity and prevent catastrophic failures. Finally, we discussed safety margins, which are the buffers engineers design into structures to handle unexpected loads. Safety margins are essential in preventing catastrophic failures, ensuring that structures can withstand more than their expected load capacity. All these elements, structural analysis, load factors, stress distribution, and safety margins, intertwine to form the foundation of structural engineering. They ensure the safety, efficiency, and functionality of everything from the chair you're sitting on to the skyscrapers that pierce the sky. The next time you cross a bridge or enter a building, remember the complex engineering principles at work. Thanks for joining us today, and we hope you've enjoyed this journey into the world of structural analysis and stress distribution.